Hey everybody, today we're going to be learning about solutions. And the first question we're going to ask is, what is a solution? Well, the definition of a solution is a homogeneous mixture of two or more substances or components. A great example of a solution is salt water. You can make a solution of salt water by taking a glass of water and adding some table salt. And what you're making is a solution of sodium ions and chlorine ions dissolved in water. And for this saltwater solution, the water is called the solvent, and the dissolved ions would be called the solute. When you're making a solution, the solvent is the majority component, whereas the solute is the minority component. So when you're making a solution, what you're doing is you're dissolving the solutes in the solvent. And so now that we have an understanding of what a solution is, let's take a look at a few different types of solutions. The saltwater example that we just looked at is an example of a solution where we dissolved a solid in a liquid. But we can also make a solution by dissolving a gas in a liquid. A great example of this is carbonated water. This is where you take carbon dioxide gas and dissolve it in water. The carbon dioxide gas is the solute and the water is the solvent. We can also form a solution by mixing a liquid with another liquid. A great example of this is any alcohols like vodka, because they're a mixture of ethanol and water. And finally, we can make solutions out of two solids. For example, brass, which is an alloy made of copper and zinc, is a solution made from two solids. So you can see there's lots of different ways that you can make a solution. But what all of these solutions have in common is that they're a homogeneous mixture of two or more substances. And now I want to focus in on a specific type of solution. These are called aqueous solutions. Aqueous solutions are solutions where water is the solvent. We already saw an example of an aqueous solution when we talked about salt water. That's a solution of sodium chloride in water. Another very common example, pop, like Coke or Sprite. These are aqueous solutions of sugar in water. And what about electrolyte drinks like Gatorade? These are aqueous solutions as well. They contain ions like sodium and potassium dissolved in water. But fair warning, water does not dissolve everything. For example, have you ever tried to mix oil with water? No matter how much stirring you do, the oil does not want to mix with the water. And now why is this? Why will some substances form solutions, but others won't? Let's start by thinking, why do solutions form in the first place? For example, looking at our saltwater solution, why does sodium chloride dissolve into sodium and chlorine ions when we mix it with water? Well, in order to understand why a solution forms, we have to look at entropy. Entropy is a measure of energy dispersal in a system. And higher entropy would mean the energy is more dispersed. And that's energetically favorable. And now if we look at our sodium chloride, you can imagine before it dissolves, it's in this crystal lattice structure. So it's very contained. But once we dissolve it in the water, it breaks apart into sodium ions and chlorine ions. And based on entropy, that is energetically favorable. So it's this tendency towards increased entropy that drives the solution formation. So entropy helps us understand why solutions form. But we still haven't answered the question as to why some solutions won't form at all. And in order to understand that, we have to look at intermolecular forces. Specifically, we want to look at the effect of intermolecular forces on solution formation. When we're forming a solution, we have our solvent and we have our solute. And we want to combine the solvent with the solute to form our solution. And now this process of solution formation has three main steps. The first step is that we want to break the bonds between the solvent particles. This allows us to separate the solvent particles and now they're available to interact with the solute. The next step is we want to break the bonds between the solute particles. So just like with the solvent, we want to break the bonds between the solute particles, so now they're available to interact with the solvent. And then the final step is that we want to mix the solvent with the solute, and this allows for the formation of new bonds between the solvent and the solute. And so what I'm saying is that for each one of these steps, there's bonds that need to be broken and bonds that need to be formed. And now where do these bonds come from? Well, for many molecules, they come from intermolecular forces, like dispersion forces, dipole-dipole interactions, hydrogen bonds, and ion-dipole interactions. And for ionic compounds, we'll have to break ionic bonds. So it's the strength of these intermolecular forces and ionic bonds that are going to determine if the solution forms. For example, let's take a look at our salt water. The solvent is water, and water participates in hydrogen bonding. So in order to separate the solvent molecules, we'll have to break hydrogen bonds. The solute is sodium chloride. That's an ionic compound. So in order to separate the solute, we'll have to break ionic bonds. And then we're going to mix the water with the sodium chloride. And what's going to happen is the water is going to hydrate the ions. So the ions are going to participate in ion-dipole interactions with the water molecules. And so this solution forms because we're able to produce new bonds between the solvent and the solute. And these new bonds release energy, making solution formation energetically favorable. And now that we're talking about the energy behind solution formation, we need to start talking about enthalpy. Enthalpy refers to the energy of the system in terms of heat. And when we make changes to the system, like forming a solution, there will be a change in the system's enthalpy. And we represent that with delta H. Now, if the system releases energy, delta H will be negative. We call this exothermic. But if the system requires energy, then delta H will be positive. We call this endothermic. And now the reason you need to understand this is because anytime we're breaking bonds, that requires energy. So in order to break the hydrogen bonds in the solvent, we're going to have to give the solvent some energy. In order to break the ionic bonds in the solute, we're going to have to give the solute some energy. But the most important thing is that when we're forming bonds, so when we mix the solvent with the solute, then we can release energy. So now if we add up the delta H's for the solvent, the solute, and the mixing, we can find the change in enthalpy for the entire solution. And ideally, the change in enthalpy for the whole solution is negative because it's energetically favorable to release energy. And even though the delta H for the solvent and the solute is positive, if delta H mix is a large enough negative value, meaning really strong bonds were formed between the solvent and the solute, then delta H for the solution can be negative. And if solution formation releases energy and the entropy of the system increases, then the solution will form. But imagine the solvent and the solute do not form strong bonds. Well, then the change in enthalpy for the solution will be positive, and more energy will be required than the energy that's released. And if your solution requires energy, then solution formation is entirely driven by entropy. So if the change in enthalpy for the solution is positive, even if the entropy of the system increases, the solution might not form. And so finally, we can understand why some solutions form while others don't. It all has to do with the enthalpy and the entropy of the solution. And now if you wanted to easily predict what combination of solvents and solutes will form solutions, you can use the saying, like dissolves like. And what this means is that substances with similar polarities will be soluble and will be able to form solutions. For example, if we're looking at water, water is polar, it has a dipole. That means it's going to easily form solutions with other polar molecules. Take ethanol, for example. It's also polar, so it has a dipole, and that means it can hydrogen bond with water. Because these two molecules can form strong hydrogen bonds when we mix them together, a solution will form. And now let's take a look at hexanes. What would hexanes want to form a solution with? Well, hexane is a non-polar hydrocarbon. It's got no charge, no dipole, so it's going to want to form a solution with another non-polar molecule. For example, hexanes will form a solution with toluene. Toluene is another non-polar molecule. And in this case, the bonds that drive solution formation are those produced by dispersion forces. And so now that we understand that, let's take a look at how some external factors like temperature and pressure can affect solubility. The first factor is temperature. We know that the solubility of a solid will increase as the temperature increases. What this means is that more solute will dissolve at higher temperatures. But if we look at gases, the opposite is true. When it comes to gases, the solubility of gases decreases as the temperature increases. And this makes sense. If you increase the temperature, the gas molecules are going to have a lot more energy. So they're going to be moving around a lot more, which makes it more likely that they're going to escape from the liquid. And gases actually have another factor that affects them as well, and that's pressure. When it comes to gases, the solubility of the gas increases as the pressure increases. And this makes sense to me. I think of pressure literally like a force pushing down on the gas molecules, holding them in that liquid. And since we're talking about pressure, let's take a look at Henry's law. Henry's law relates the solubility of a gas to the partial pressure of the gas above the liquid. And this is the equation you can use to answer Henry's law questions. This equation states that the solubility of a gas is equal to the Henry's law constant times the partial pressure of the gas. And now it's important to understand where this equation came from. This equation comes from the fact that the process of dissolving is an equilibrium process. In terms of gases, this means an equilibrium is established between the gas that's dissolved in the liquid and the gas that's above the liquid in the container. In regard to ionic compounds like our sodium chloride solution, an equilibrium would be established between the sodium and chlorine ions that are dissolved in the liquid and the undissolved solid sodium chloride. And now what Henry's law states is that as the partial pressure of the gas above the liquid increases, the solubility of the gas in the liquid will increase as well, because the additional pressure has changed the equilibrium so that it favors more dissolved gas. Now let's do a quick question to practice using Henry's law. Alrighty, in this question, we want to know what pressure of carbon dioxide gas is required to keep the carbon dioxide concentration in a can of pop at 0.12 molar. I know I have to use Henry's law because we're talking about pressure and concentration of a gas. And since we want to determine the pressure, all I have to do is rearrange this equation to solve for pressure. And now I can plug in my values for the solubility of the gas, which is just the concentration, and then plug in the value for Henry's law constant. And it's important to note that this value only applies to carbon dioxide gas at this temperature. And then when I do the math, I can see that the pressure of carbon dioxide gas has to be 3.5 atmospheres. And so what this means is that the pressure of carbon dioxide gas above the liquid has to be 3.5 atmospheres for the concentration of carbon dioxide gas in the liquid to be 0.12 molar. And now we're at the final topic in this lesson, which is solution concentrations. When we're trying to figure out a solution's concentration, what we're trying to determine is how much solute is in a solvent. And there's a whole bunch of ways that we can express concentration. The first is molarity. Molarity is found by taking the number of moles of solute and dividing that by the volume of the solution. And molarity has units of moles per liter. Then we have molality. Molality is found by taking the number of moles of the solute and dividing it by the mass of the solvent. And molality has units of moles per kilogram. The next way to express concentration is using the mole fraction. To find the mole fraction, you have to take the number of moles of the solute and divide it by the total number of moles, which would be the moles of the solute plus the moles of the solvent. And the mole fraction is unitless. And now we can also find the mole percent, which is just the mole fraction times 100%. Then we have parts by mass. So we take the mass of the solute and we divide it by the mass of the solution. And once we've done that, we can multiply it by a multiplication factor. So if you want to find the percent, the multiplication factor would just be 100. If you need to find the parts per million, which is ppm, the multiplication factor would be 10 to the 6. If you need to find the parts per billion, so ppb, the multiplication factor would be 10 to the 9. And the last way that we can express a solution's concentration is using parts by volume. That's when you take the volume of the solute and divide it by the volume of the solution. And then you'll need to multiply that by a multiplication factor, which again would be 100, 10 to the 6, or 10 to the 9, depending on if you need the percent, the ppm, or the ppb. And so those are all the different ways that you can express a solution's concentration. And now let's do an example to practice using some of these equations. Alright, so in this question, we want to prepare a solution by dissolving 18 grams of ethylene glycol in 0.5 kilograms of water. The final volume of the solution is 515 milliliters, and we want to calculate the molarity, the molality, the percent by mass, and the mole fraction. Let's start with molarity. Molarity is the number of moles of solute divided by the volume of the solution. And remember, molarity has units of moles per liter. Now, in order to find the molarity, we first need to calculate the number of moles of solute. You can find the number of moles using this equation, where the number of moles is equal to the mass divided by the molecular weight. The mass of ethylene glycol was 18 grams, and the molecular weight of ethylene glycol is about 62.07 grams per mole. And with that, we can find the number of moles of solute, which is 0.29. We just need to divide the number of moles of solute divided by the volume of the solution. And remember to convert the volume into liters. And with that, we can see that the molarity of the solution is 0.56 moles per liter. Now let's find the molality. The molality is the number of moles of solute divided by the mass of the solvent. And remember, the molality has units of moles per kilogram. This one will be pretty easy for us because we already know the moles of the solute and the mass of the solvent. And so we can quickly do the math and see that the molality of the solution is 0.58 moles per kilogram. And now we can find the percent by mass. This is the mass of the solute divided by the mass of the solution, and then multiply that by 100%. The mass of the solute is just 18 grams, and then the mass of the solution is the mass of the solute plus the mass of the solvent. And make sure you have everything in the same units. And when we do the math, we can see that the percent by mass is 3.5%. And what this means is that by mass, there's 3.5% ethylene glycol in this solution. And now we need to find the mole fraction. The mole fraction is the number of moles of the solute divided by the total number of moles, which would be the sum of the number of moles of solute plus the number of moles of solvent. Now we don't know the number of moles of the solvent, but we can use this equation to solve for it. We just need to take the mass of water divided by the molecular weight of water, and that gives us the number of moles of solvent, which is about 28 moles. And then we can just plug our values into the mole fraction equation, and we can see that the mole fraction for ethylene glycol is about 0.01. And so that's a few ways that you can find the concentration of a solution. And with that, we're done this lesson on solutions. I know it was a long one, but I hope you have a better understanding of what a solution is, the different types of solutions you can form, how do solutions form, why do some solutions not form, and what factors affect solubility. Thank you for listening and have a great day.